We've been talking about the k nearest neighbors algorithm. In this class, let's go into a few nitty-gritty details of implementing the k nearest neighbors algorithm. Let's first recap what is the k nearest neighbors. We represent all our data points as points in an n-dimensional hypercube. Then, when a new data point comes in, which is called a problem instance, this is also represented in that n-dimensional space, and the problem now is to figure out which category to classify into. Say in the case of emails, is it a spam email or a ham email? The way k nearest neighbors works is it finds, as the algorithm's name says, the k nearest points to this problem instance. If most of these points or all of these points are spam, it will mark the problem instance as spam. Another data point comes in, another problem instance email. If the k nearest neighbors or the majority of those k nearest neighbors for this point are ham, it will mark it as a ham email. This is basically the k nearest neighbors algorithm. Now, as you could see, k nearest neighbors is simple enough to visualize. But there are a few wrinkles that we need to understand. What should be the definition of distance? How do we say that this point is nearer to this set of points? Clearly, k is an important parameter. How do we choose k? What if there are too many dimensions? How do we reduce the number of dimensions to make it more computationally efficient? How do we use k nearest neighbors in prediction? And what if there's a large amount of data? How do we work efficiently? Let's talk first about dimensionality reduction. Dimensionality is basically the length of the feature vector that we use. So, if you're in an n-dimensional space, or if you're representing your problem instances in an n-dimensional hypercube, then you need n coordinates to express each point. That's the dimensionality. Now, as the dimensionality increases, both the efficiency and the efficacy of the k nearest neighbors reduces. The efficiency suffers because finding the point-wise distance between very high dimension vectors is highly computationally intensive. It would require element-wise operations on this high number of dimensions. Efficacy can also suffer because in such a high dimensional space, it might be really difficult to differentiate between points. So, they might all seem to be approximately equidistant. So, for these reasons, dimensionality reduction becomes something really key to the k nearest neighbors implementation. Before you go ahead with the implementation of the algorithm, you need to reduce the number of dimensions of the feature vectors. Dimensionality reduction in this case is done using feature extraction. This is basically a process to create new features of lower number of dimensions using some technique like principal components analysis. Another smart way to do dimensionality reduction is to use hashing. So we could use a hash function to map similar items to similar buckets. Hashing is really useful because it can map these items to a lower dimensional space without losing any information about the individual points. One way to do this is locality sensitive hashing, which basically treats points which are nearby each other as similar. Now, another important decision to make is the definition of distance. Euclidean distance is a simple and common way of computing distance in geometry. In 2 and 3 dimensional spaces, this is the physical distance between the 2 points, and the formula can be easily extended to n dimensions. But this is not always a suitable definition of distance for the k nearest neighbors implementation. Usually in k nearest neighbors, the algorithm uses weights. It modifies the distance formula to downweight the importance of points which are farther away, and it increases the importance of the points which are nearby. Also, Euclidean distance really only works in the case of continuous variables. So if your feature vectors are made up of variables that are continuous, then you can use Euclidean distance. But if they're made up of variables that are discrete or categorical, then Euclidean distance doesn't work. Letters or words or colors are examples of variables that are categorical or discrete. In the case of discrete variables, you could use a distance measure like the edit distance or Hamming distance. How does edit distance typically work? It would be the number of edits required to go from one string to the other. So this is the minimum number of changes that you need to make so that you can make one string the same as the other. We've talked about dimensionality reduction and the definition of distance. Let's talk about the choice of k, which is clearly an important parameter in the k nearest neighbors. The process of choosing the right value of k is called parameter selection. Now, an important special case is k equals 1. This is called the nearest neighbor algorithm. Choosing k is particularly tricky. If you choose a large value of k, then you could help reduce the effect of outliers in your data. The points which are rather far away from the cluster and are likely to be misclassified would be correctly classified. But the larger the value of k, we also increase the chances that we pull in a large number of instances that are of the other category. So how do you choose the right choice of k? A lot of research has been devoted to it, and you could read up on it over the internet and look at a bunch of papers which have been written on this topic. We'll leave it at that in this class. Let's move on to data reduction. We've already spoken about dimensionality reduction, which is basically reducing the number of dimensions in our feature vector so that we can become computationally efficient by reducing the number of coordinates needed to represent each data point. But what if the number of data points itself is too huge to do anything with? Now, in k-nearest neighbors, it's important to reduce the amount of data, to lose the junk, the data that doesn't really add to the learning process. So basically trim the number of data points wherever possible. Same as with dimensionality reduction, getting rid of the right set of data points will improve both the efficiency and efficacy of the k-nearest neighbors implementation. A common way of going about data reduction is to divide all your data points into 3 categories. Let's talk about what each of these categories are and how they are significant. The first category is prototypes. These basically represent the training data particularly well. Prototypes in the training data can be identified using some prototype selection algorithms which are standard. The next category is class outliers. Once you've identified the prototypes using a prototype selection algorithm, you would go ahead and classify all the training data using these prototypes. Now, the class outliers are the points in the training data that are not correctly classified using our selected prototypes. And the absorbed points are the points that are correctly classified using the selected prototypes. Now, what the data reduction technique does is it keeps the prototypes in order to continue the classification, drops all the absorbed points because they're not really adding much in terms of information, and selectively keeps some class outliers. Now, till now we've been talking about k-nearest neighbors as a classification algorithm, but we could use it as well to do something like predict something about the new instance, some particular measure or value. So as we've been talking about how KNN works, given a problem instance, which is a point to be classified, we check what are the k nearest neighbors and which category those neighbors belong to, and we assign our problem instance to whichever category the majority of the k nearest neighbors belong to. Now, we could just as easily use these k nearest neighbors to predict the value of a function for this problem instance. We'd simply calculate the value of the function for the k nearest neighbors and then extrapolate the value of that function for our problem instance. For example, we could use the mean of the value of the function for the k nearest neighbors to predict the value of that function for the problem instance.